Hello, welcome back. This is 10.3 on multiplying and simplifying radical expressions. In particular, we'll begin today with the product rule. Product rule. And what this says is that the product of two nth roots is equal to the nth root of the product. Okay, so we can rewrite, if you have two roots being multiplied by each other, you can rewrite it as one root. Okay, kind of combine it into one thingamajig like that. Okay, so why can I do this? We can explain it by converting everything into rational exponents and then using our rules of exponents. Okay, so first, the nth root of a is the same as a to the 1 over n. The nth root of b is equal to a to the b to the 1 over n. And then we could kind of use the reverse of our product to power rule, which I'm doing over here at the top right. So instead of at the top right, I would distribute the x, but if you kind of think of it in reverse, what you're doing is kind of factoring the x out of the exponent. So you'd end up with ab to the 1 over n, and then you could rewrite that thing as the nth root of ab. Okay, so let's take a look at applying this rule to some problems. Here we have the square root of 7 times the square root of 5. That will be the square root of 7 times 5. So let's just write 35, right? Number 6, here we have the fifth root of 9 times the fifth root of 3. So because we have the, you can't necessarily do this with different roots. Okay, it won't work. But here we can. We have the same root, so we can rewrite it as the fifth root of 3 times 9, which is 27. Okay, here's 14. So we have a binomial this time inside our roots. So the sixth root of x minus 5 times the sixth root of x minus 5 to the fourth. Okay. So we can rewrite this as the sixth root of x minus 5 to the 1 plus 4, which is 5, right? Just adding exponents using our exponent rules. Okay, let's look at one more. Here's number 20. We have the ninth root of 12x squared y cubed times the ninth root of 3x cubed y to the fourth. Okay, so I have the same type of root. I can combine everything together. 3 times 12 is 36. And then for the rest, you're just adding exponents, right? So you have x squared times x to the cubed. That would be x to the fifth. Y cubed times y to the fourth would be y to the seventh. Okay. Okay, so after we get a handle on that, we'll want to simplify. And basically what you'll do is factoring. So simplifying these expressions now after we multiply them out. And it'll come down to just marching out all of your perfect squares. Okay, so march out the perfect squares. Okay, so let's take a look here. I got 22. So let's say our product resulted in a square root of 27. So what we're going to do is factor 27 into 9 times 3. Okay, and then you could kind of quote unquote march out the square root of 9. But using this multiplication rule, excuse me, kind of in reverse, what we're actually doing is splitting this into two square roots. And then just taking the square root of 9, so I give you 3, and then the square root of 3. So you always, well, not always, but sometimes you'll have some leftovers. Okay, let's look at more of these. The simplification process. So here I have the square root of 28. 28 is 4 times 7. So hopefully you have in the back of your mind kind of a foothold on the perfect squares. So this would be the square root of 4 times the square root of 7. And of course the square root of 4 will just be 2, and then you get times the square root of 7. That's kind of your leftover. Let's try 28. Here we have the cube root of 54. Okay, so cubes, perfect. I'm factoring 54, right? So I want to factor it into something that's a perfect cube. And I've been working with these perfect cubes in the previous section, so I kind of know what they are. There's like 8, 27, 64. So I'm hoping to see one of those numbers pop out. So 54 is 2 times 20, and there, sure enough, there's 27 is a perfect cube. So I'm going to kind of put that guy in the front, and I can then split up my cube root accordingly. And then the cube root of 27, of course, is just 3, and I should have a little 3 on that cube root of 2, like that. Okay. Let's look at another one, 32. Here now I have the cube root of negative 32x squared y cubed. Okay. When you're dealing with variables, you want to look for exponents that are divisible by 3. Okay. So in this case, I'm not going to be able to do anything with that x squared, but the y cubed, I'm going to be able to take the cube root of that. All right, and I'll talk more about that in this sort of next section that we get into. But anyways, for now, let me rewrite it by factoring. So 32 is the same thing as negative 8 times 4, where negative 8 is a perfect cube. The x squared, I can't really do anything with that, but y cubed is a perfect cube, so I'm going to be able to factor that out. Okay, so let me rewrite it, kind of putting the perfect cubes up front now in anticipation of giving them their marching orders. Oops, need to extend this a little bit. And then I can split up the cube root. And in practice, I really don't show the step that I'm writing out right now. I'll just kind of do that in my head. But in the beginning, you want to kind of show it. Okay, and then you have the cube root of negative 8. It's negative 2 times negative 2 times negative 2 gives you negative 8, so it's negative 2. The cube root of y cubed was just y. You're asking yourself, what times what times what gives me y cubed? It's just y. And then you kind of have some leftover bits here, 4x squared. Okay. Let's look at 34. This time they want you to simplify this function. The function is 81 times x minus 2 squared. All right, we can kind of split it into 2 square roots and look at each one individually. Square root of 81, we all know that's just 9. The square root of x minus 2, if they've not made any restrictions on the variables, you're going to have to include absolute values on that guy. So it's going to be absolute value x minus 2. Okay. In general, though, they're going to say that they're restricting their variables so that they're positive. Okay. So in general, if you're dealing with these non-negative quantities, so simplifying with non-negative quantities. In those cases, you don't have to worry about the square roots, I mean the absolute value things. If you have the nth root of a to the n, regardless if n is even or odd, that's just going to equal a. Okay. All right, so let's look at some of these. 40, we have the square root of x to the 5th. Okay, so this will be the square root of, I want exponents that are divisible by 2. So 5 is not divisible by 2s, but I can kind of create an exponent that's divisible by 2 via factoring, right? Because x to the 5th is the same as x to the 4th times x. Okay, and then I can go ahead and march the x to the 4th out. And to do that, you just basically divide the exponent by whatever the index of the root is. In this case, the index is 2, right? We don't see it, but it's there. So what you would end up with is x squared being marched out. because x squared times x squared is x to the fourth, right? And then you get the leftover part, which you can't do anything with. Let's try another one. So I have square root of 40 x cubed. Okay, so I'm going to factor this. 4 is a perfect square times 10, and then x cubed I'm going to rewrite as x squared times x. And then you kind of see, all right, this guy is a perfect square, this guy's a perfect square. I'm going to march those guys out. Square root of 4 is 2. Square root of x squared is just going to give me x. And then I have the leftover parts inside my root. Okay. More examples. Number 48 here. You have the cube root of x cubed y to the 17th z squared. Again, I'm looking for perfect cubes and things that are divisible by have exponents divisible by 3. So x cubed is good to go. We're going to march that out. But y to the 17th, I can't do anything with that as is. So I have to factor it into y to the 15th times y squared. So it's not only that you want the exponent to be divisible by 3, but you want the biggest exponent that's divisible by 3. So I wouldn't factor it into y to the 12th times y to the 5th, right? I need the biggest one, so y to the 15th times y squared. And then the z is kind of stuck. That's not a perfect cube. We can't do anything with it. Okay, so I'm going to be able to march this guy and this guy out. I'll end up with x y to the 5th times the cube root of y squared z squared. Okay, let's try one more. And then we'll kind of work with multiplying and then simplifying. Okay, so here we have the 5th root of 64 x to the 7th y to the 16th. And again, I'm looking for perfect fifths. So what is 64? Over here to the top right, 2 times 32, 2 times 16, 2 times 8, 2 times 4, and that's 2 times 2. So we have 1, 2, 3, 4, 5, 6 2's. And you could always rewrite 64 as 2 to the 6th. Okay. And then we have x to the 7th, y to the 16th. I want perfect fifths, basically. Exponents that are divisible by 5. So I'm going to have to factor 2 to the 6th and the 2 to the 5th times 2 to the 1st. And then x to the 7th, I'm going to make x to the 5th times x squared, running out of room. And then x to the 16th, y to the 16th, I'm going to write as y to the 15th times y. Okay, and then hopefully it's clear what my perfect fifths are. This guy, and this guy. Okay, so I can march those out. I'll have just 2x y to the 5th. Or sorry, y to the 3rd. 15 divided by 5 is 3. And then I have the 5th root of the leftover bits, 2x squared y. Okay. Okay. Now we kind of return back to where we started at the beginning. We're going to multiply using our product rule for radicals and then simplify. Kind of where I initially thought we were headed, but we had to take a bit of a detour first. Okay, so number 62, I'm looking at, I have the square root of 3 times the square root of 6. Okay, alone, neither of these are going to be factorable or in any way simplifiable, so what we do is rewrite it. 3 times 6 is 18, and then we could factor that into a perfect square, particularly 9 times 2, and then we can march out the 9, right, because 3 times 3 is 9, so we'll have 3 root 2. Okay. So it's kind of weird. At first it doesn't look like we can simplify it all, but then when you multiply it out, yeah, we can. Let's get another 20x times the square root of 5x. That'll equal the square root of 100 x squared. Both of those are perfect squares, right? 10 times 10 is 100. X times x is x squared, so we can just completely get rid of the square root, and we'd have 10x. This last one's the video quiz, and then we'll jump into my math lab. So video quiz. Here we have the cube root of 6x to the 7th times y times the cube root of 9x to the 4th y to the 12th. Okay. So again, I'm going to kind of multiply it out first. So 9 times 6, I believe it's 54. X to the 7th times x to the 4th. You add the exponents, you get x to the 11. Y times y to the 12th. Adding exponents, you get y to the 13th. Okay. 54 is 27 times 2, 27 being a perfect cube. Okay. X to the 11th, we'll have x to the 9th times x squared. Y to the 13th, I'll make y 12th times y. Okay. And then visually looking for perfect cubes, those guys right there, march them out. So 3x to the 9 divided by 3 is 3, y to the 12 divided by 3 is 4, and then you get your leftovers, 2x squared y. Okay. Okay, so there's a video quiz. And now I'm just going to jump into my math lab and do a whole bunch of problems so you can watch, or you just use it as reference. It's up to you. Okay. Okay. So my math lab. Let me rearrange my desktop here. And take a look. Okay, so yeah, the first, problems, all you're doing is multiplying out using the product rule. No simplification involved in most of these. So square root of 13 and square root of 2 is square root of 13 times 2, which is square root of 26. I wonder if it tells me which ones I got right. Same deal here. All you're doing is just multiplying out and then putting them inside the root. Let me get rid of this thing. Just work with this guy. Let's look at question 5. Yes, this one's a little bit different. X plus 11 times the square root of x minus 11. You may think that you can simplify this, but if you can't. Right, so you would need x plus 11 times x plus 11 to simplify. In this case, that's not possible. So anyways, when you multiply out, you're foiling, so you'll get x squared plus 11x minus 11x is 0x. And then 11 times negative 11 is 121. And then you would just put that in there. You could see my answer there, square root of x squared minus 121. There's nothing else you could do. So that one's just a bit weird. Let's look at 7. Some fractions. I didn't really talk about fractions in the video so far, but it's no big deal. You just multiply them out, right? So you get the square root of 2x times 7 all over 7 times 2. Then you can remove common factors. You're going to end up with the square root of x over 1, or square root of x. Okay. Was that number 7? Let's get number 8. Same deal here. 8th root of x over 5 times the 8th root of 7 over y. Multiplying out these fractions, you go just straight across. 7x over 5y, the 8th root of that. Later we do rationalization in later sections. You don't have to do that here though. 8, 9. Now we're in the simplification problems. So 45, you want to factor it so you have a perfect square that you can march out of the root. So 45 is the same as 9 times 5. And then you could, this guy is, square root of 9 is 3. So you get 3 square root of 5 for your answer. Let's look at 14. Sure. So this one, because they say x can be any real number, you have to include the absolute values with your answer. Okay, and I did an example like this in the lecture video here. But anyways, square root of 121 is 11. Square root of x plus 2 squared, you're going to need an absolute value. Okay. So that would be 14 and then 15. For cube roots, you don't need absolute values, right? It's only when you have an even powered root that you need to worry about it. So this cube root is 16 times x plus 9 cubed. The 16 itself is not a perfect cube, but 8 is. So you go 8 times 2 times x plus 9 cubed. And then march out the cubes, the perfect cubes, those two. So you're going to end up with 2, and the way I wrote it is maybe a little bit weird, but I always kind of put the numbers up front and variables towards the back. Okay, so 2 cube root of 2, so it's 2 times the cube root of 2 times x plus 9. And you kind of see why I put those hooks on my radicals, so I don't accidentally think that the x plus 9 is underneath the radical. Okay. So what is that, 15? Let's look at 16. For this one, you have to factor it first before you can see what's going on. So factor out the 13. I get x squared minus something plus something. I need to use my calculator to get them. Okay. So 234 divided by 13 is 18. X, and then 1053. Really? 13. 81. And then I can factor that thing. So I get the square root of 13 times x minus 9, x minus 9. So it's x minus 9 squared, which is a perfect square, which you can then march out of the root. Okay, so you're going to end up with the square root 13 times x minus 9, but that x minus 9 has to be in absolute values because it's a square root of something squared. And it says assume x can be any real number. So when you see that, you have to get the absolute values involved. 16, 17. So this is just simplifying, marching out perfect squares. So x to the 9th, I need to rewrite that as x to the 8th times x. I'll get y to the 4th. And then you see your perfect squares right there and there. Factor those guys out. So get x to the 4th, y squared, squared x. 17, 20. Perfect cube, just simplifying. 16 x to the 17th, y to the 9th. 16 is the same as 8 times 2. 8 is a perfect cube. And then x to the 15th times x squared, and y to the 9th is a perfect cube already. So these guys can be marched out. So I'm going to get 2x to the 5th, sorry about the color, y cubed, and then cube root of 2x squared left over. It's 20, 21. The 5th root of x plus y to the 6th. I want to rewrite it, so I have a perfect 5th in there. So I'll rewrite x plus y to the 5th times x plus y to the 1st. And then you can remove this perfect 5th. Okay, so that would give you, oops, wrong color, x plus y times the 5th root of x plus y. Okay. You can tell now you don't have to worry about absolute values because of this big statement. Assume that all variables in the radicand represent real positive numbers and the radicand does not involve negative quantities. That just means no absolute values. Okay. You wouldn't need them here because we have an odd root, but you do need it for other questions in this set. Okay, let's move on. Multiplying out and then simplifying. So, yeah, I mean, you can literally read this as 5 times root 3 times 4 times root 24. and then use the commutative property to rewrite it as 5 times 4, which I would never show, but just for the sake of teaching, I do show it. And then 5 times 4 is 20, and then you get the square root of 3 times 24. Let's rewrite that though so we can see the perfect squares. So 24 is the same as 4 times 6, so we get 2 times 2 times 2 times 3. So it looks like I'm getting 2 times 2 times 2 times 3. And then you could kind of group the perfect squares together. So there's 9, and then there's 4. Okay, so let me rewrite it so you can see that. Square root of 3 times 3 is 9, and then there's that 2 times 2 gives me a 4, and then there's the leftover 2. Okay, so I'll have 20 times square root of 9 is 3, times square root of 4 is 2, times the square root of 2, and then multiply all those leading terms out. 20 times 3 is 60, times 2 is 120, square root of 2. Okay, that was 29. Let's look at 33. Oof. So they just get worse and worse, right? So 16 x to the 7th, y to the 7th, z to the 13th, times the 5th root of 4x to the 6th, y to the 4th, z. And so we get the 5th root of 4 times 16 is 64. I should rewrite that as a power of 2. So again, 16 is basically 2 times 2 is 4, times 2 is 8, times 2 is 16. It's 2 to the 4th. 4 is just 2 squared, so we'll end up with 2 to the 6. And then x to the 7 plus 6 is 14. No, 13, sorry. Y to the 7 plus 4 is 11. Z to the 13 plus 1 is 14. And then we're looking for perfect fifths. So we get 2 to the 5th times 2 to the 1. X to the 10th times x cubed. Y to the 10th times y. Z to the 10th times z to the 4th. Okay. And then we're marching out the perfect fifths. So this guy, this guy, this guy, this guy. Okay, so we'll get 2x squared, y squared, z squared times the 5th root of 2x cubed y z to the 4th. That's 33. 37. So look at that one. So we have 2x squared y times the 4th root of 8x to the 6th y times negative 3xy squared times the 4th root of 2x to the 9th y squared. Okay, so first I'm going to multiply out the non-radical stuff. So I get negatives, and you could do that using the commutative law. You just have to kind of switch everything around. But anyways, you get negative 6x cubed y cubed. And then let's go to our 4th root. So 8 is really 2 times 2 times 2. So it's 2 cubed times another 2 will give me 2 to the 4th. Then we get x to the 6th times x to the 9th is x to the 15th. And then y cubed. So I can march out the 2 to the 4th. Oops, I'm going to have to factor the x to the 15th. So negative 6x cubed, y cubed, times the 4th root of 2 to the 4th times x to the, what do we need? 12 times x cubed times y cubed. And so then we can march out the 2 to the 4th and the x to the 12th. Negative 6x cubed, y cubed times 2 times x cubed times the 4th root of x cubed y cubed. And then you could rearrange things using commutative law. Negative 12 x to the 6th y cubed times the 4th root of x cubed y cubed. Let's go on to the next one. Got some functions, some story problems here. Okay, so the function d of x models the distance d of x in miles that a person x feet high can see to the horizon. A deck on the beach is 98 feet above the water. How far can the person see? So x represents the number of feet that high that the person is. So in this case, the person is 98 feet high. They want to know the distance this person can see, so you're going to plug 98 into this expression. And you get the square root 3 times 98 all over 2. 98 over 2. So 2 goes in the 98 49 times. So you'll get 3 times 49. And then you can march out the root 49, make that 7 root 3. Okay, so you can see that in miles. And then they want you to actually put it in your calculator and get an approximation. Okay, so it would be 12.1. This guy is kind of annoying. I remember doing this one. Paleontologists use this function, w of x is 4 root 2x, to estimate the walking speed of a dinosaur, which is wx, in feet per second, where x is the length in feet of the dinosaur's leg. So if you know the length of the dinosaur's leg, you can figure out how fast it walks. What is the walking speed of the dinosaur whose leg is 6 feet? So you're just putting 6 in there, and you get 4 root 2 times 6. Okay, so you get 4 root 12, but you could rewrite 12 as 4 times 3 and then factor out square root 4. That will be 2, so you get 8 root 3 feet per second. Yeah, they want radicals. And then this is the weird part where they want you to estimate the walking speed using the graph. So I advise you to kind of pop it out like that. And then be careful because the y-axis is in 2's, not 1's. So I made that mistake already. I need to go to what, 6 to do the same thing. So I'm going to kind of move this over here and move this over here. So 1, 2, 3, 4, 5, 6, and then you're kind of looking for where this hits, and it should be about right here, but you got to be careful that the thing is going in 2's, right? So it's 2, 4, 6, 8, 10, 12, looks like 14 is right here. Okay, so just be careful on that one. It's easy, it's silly, and it's a headache if you don't get it right. But anyways, there's that, and thanks for watching, and we'll see you next time.